Hey, you guys, we're going to get started here in just a minute. So I hope you guys are enjoying your day off. We have a couple requests already for topics to cover. So again, I'll cover them in order of how they kind of have been requested already. Hopefully you guys can all hear me. I left my periodic table at home, so I'm going to be referencing a periodic table that I have online, and I think it's going to be rounding to the same as what we already have. So please excuse the fact that there may be several differences, and if you guys notice something, feel free to point it out if I'm using like a number that doesn't seem right. So just before we get started, what I want to briefly just talk about is what is going to be on the test. So just thinking back of the topics that we have covered. So we started off this unit talking about the mole, and we talked about the idea of how big the mole is. And we said we can use the mole as what's called a counting unit. So we can refer to it as anything, meaning 1 mole could equal 6.02 times 10 to the 23rd shoes, or pencils, or just a wide variety of things. And then we did some calculations with that. And then what we did is that we used that, and we used the idea of molar mass. So we said, okay, now it's more practical to talk about the measurement of a mole of an atom or a mole of a compound, because we can actually measure those. We can't measure a single atom or anything like that. So it's easier to do those. And so we looked at some calculations where we're going from moles to molecules, or moles to grams, and things like that. We then started talking about ionic, covalent, and metallic bonding. We talked about the difference between those bonds and those compounds. And then we went into naming those. So we have different systems of naming for ionic, covalent, and acids. So we talked about those 3 types of naming. And then we got into some more math. So then we started talking about calculating the molar mass of compounds, and the percent composition, and empirical and molecular formulas. And so that was the homework that we did and that we went over on Thursday. So to begin with, I'm going to talk a little bit about balancing reactions, just to kind of give us an overview of how to balance reactions and things like that. Let's see, I'm going to go back to a problem. All right, so let's look at a reaction that we can balance. Okay, so I'm going to do some from the homework. So this is going to be balancing reactions. So let's look at a formula like, let's say that we have Al2O3, and this is a solid, and we want to write, let's say that we want to write the formation. So the reaction of formation for this, for this compound right here. This is an ionic compound, and the reason we know it's an ionic compound is because it has a metal in there. It's aluminum. So if we break this apart, what we know is that this aluminum oxide comes from aluminum, and aluminum is a solid. And it also comes from oxygen. And what we want to remember about oxygen is that oxygen's a diatomic, so we would never see it by itself. And at room temperature, it's a gas. And so these 2 things would react, and this would be our reaction of formation, to create aluminum oxide as a solid. Now, what we see with this reaction is that it's not balanced. We have 1 aluminum over here. We have 2 aluminums over here. We have 2 oxygen atoms over here. We have 3 oxygen atoms over here. So we need to balance this reaction. And the way that I like to balance reaction is I say that I like to take my inventory. So I write down the species that I have on each side. So I have aluminum, oxygen, and then I write down how many I have. So over here as a reactant, I have 1 aluminum. Over here, I have 2 aluminum. Over here, I have 2 oxygen. Over here, I have 3 oxygen. And so what I'm going to do is I'm going to start adding what are called coefficients. So I need to add numbers out in front, whole numbers, in order to balance this reaction. So if I look at aluminum right here, what I see is that I need to have 2 aluminums on this side. And so the only way to do that is to multiply this by 2. So if I multiply that by 2 and I put a 2 in front of there, now my aluminums are balanced. We go on and we see that oxygen is not balanced. So we have 2 and we have 3. Now these have to be whole numbers, and the number of oxygen atoms also has to be a whole number. So when we have something like 2 and 3, what you want to think about is what is the lowest common multiple of 2 and 3? And what we see is that it's 6. So that means that I want 6 oxygen atoms on each side. So the only way to get 6 oxygen atoms on each side is to multiply this by 2. Notice that that changes my number of aluminum, and it changes the number of oxygen. And then over here, I want a 3. Now my oxygens are balanced. I just need to go back one more time and change my aluminum. So now what I see is that aluminum, I don't want 2, I actually want 4. And so there is a balanced chemical reaction for the formation reaction of aluminum oxide. We'll go into this in more details. It's these are kind of like basic ones where they're fairly straightforward to balance, but there are ones that get a little bit more tricky. So we will go ahead and hopefully that answers the question about balancing reactions. There was another question about naming compounds, specifically acids. So I'm not going to go over naming all the compounds, all the different types of compounds, unless you guys give me certain examples. So I'm just going to go ahead and go over some different types of naming compounds or different types of acids. So let's talk about acids. If a compound ends in ate, well, actually, let me start with ide. If my compound, not ate, let's start with ide, ends in ide, it's going to become a hydro, and then kind of ... ic acid. An example of this would be HF. This is fluoride. And so this acid becomes hydrofluoric acid. And I spelled fluoride wrong. Sorry, you guys. So hydrofluoric fluoric acid. So that's if it ends in ide. If they end in ate, this is not going to have the prefix hydro. It's just going to be, I'll put ... an ic acid. So an example of this would be, let me think of something off the top of my head. Let's look at this. So H2SO4. This right here is sulfate. So we see it has that ate ending. And so if I were to name this, this would be sulfuric acid. So notice that I changed that ending to an ic. And then if I have an ite, let's see, let's do HNO3. Whoops, I moved ahead of myself. Hold on, let me go back. If I have ite, I'm not going to have an ic, but it's going to be an OUS acid or an US acid. So my example would be something like HNO3 or NO2, excuse me. And NO2 is nitrite. So we see it has that ite ending. And so this would become nitrous acid. So those are how we name them and some examples of going from the formula to the name. So let's just look at a couple different other ones. And let's say that we're going from the name to the formula. So let's say that we have hydroiodic acid. Let's say that we have carbonic acid. And let's say that we have sulfurous acid. So if we look at these three acids, what we want to look at is we want to look at how they're named. So this is a hydroic acid, which means that it comes from ide. That means that this comes from iodide. And iodide is I with a -1 charge. If this becomes an acid, we need to balance this with hydrogen. And since this has a -1 charge, and if we were to add a hydrogen, that would be a +1 charge, what we see is it says HF. So this is hydrofluoric acid. All right, an ic acid comes from 8. So if this is 8, this means that this comes from carbonate. And carbonate is CO3 with a 2-. So if that's CO3 with a 2-, that means that we need to add 2 hydrogens to this. So this is going to be H2CO3. All right, and sulfurous. So sulfurous, the S comes from ite. So this comes from sulfite. And sulfite is, whoops, hold on. It's not that. Sulfite is SO3 with a 2-, I want to say. You guys can correct me if I'm wrong, but I'm pretty sure it's a 2-. And so what this would be H2SO3. So notice that that ending tells me what the anion is, the negatively charged particles. And so then I just need to add hydrogen in order to balance it out. All right, other questions that I have are coming from the homework. So I'm going to answer a couple homework questions. So the first one being, let's look at number 7 on the homework. So number 7 on the homework. Whoops. Hold on one second. I opened something. Okay. Okay, number 7. Number 7 on the homework says that you have 4 grams of mercury chloride is heated. After heating, 3.43 grams of product remains. What are the possible formulas for mercury chloride? So first of all, for 1A, what it's asking you to do is it's asking you to write the 2 formulas for mercury chloride. So you either have one of 2. You could either have mercury 1 chloride or you could have mercury 2 chloride. So you're either going to have Hg2Cl2 or you're going to have HgCl2. So these are your 2 options. And again, those come from your 2 different ions of mercury. And so the next question says, find the percent composition of mercury chloride. Part B is a little tricky. And the idea with this, and I wouldn't expect you to know this on a test or a quiz, but when we heat mercury, so if we have, let's say we have mercury, let's call this X, chloride Y, because we don't know what these are. When we heat this, we're actually going to get mercury and we're going to get some chlorine. And this chlorine is going to be a gas. And so when we heat it, I'm going to put this delta sign. This means heating. So when I heat this compound, what happens is that it breaks apart. And so when they say that we have 4 grams of mercury chloride and it's heated to and 3.43 grams remain, what that means is that the total amount of mercury that I have is 3.43 grams. And the amount of chlorine I have, whoops, I forgot to put my 3. The amount of chlorine I have is, well, if I start off with 4 grams and I know that 3.43 grams of that is mercury, that means that the rest of it, 0.57 grams, is chlorine. And so now what we can do is we can calculate our percent composition. So to find your percent of mercury, I'm going to take my 4.43 grams and I'm going to divide it by my total mass. And to find my percent chlorine, I'm going to take my mass of chlorine and I'm going to divide it by the total amount of the whole sample. So notice I'm doing my part over my whole. I'm going to multiply these both by 100 to get a percentage. And what I end up getting is 85.8%. And then I get the rest of this, which would be, let's say, 14.2% for the rest of my compound. And so then the rest of this asks you to find your empirical and molecular compound for this. So let's go ahead and look at that. So if we were to find the first empirical formula, so we have, this is part C, we're going to find the empirical formula. So my empirical formula, I need to figure out the grams of mercury. So I'm going to take my mass of mercury, 3.43 grams, and I'm going to multiply that by the molar mass of mercury. And the molar mass of mercury, according to the periodic table that I'm looking at, is 200.6 grams of mercury per 1 mole of mercury. So my units cancel out, and I'm going to get my moles of mercury. And so what I get is 0.0171 moles of mercury. And so then what I do, I go ahead and I look at chlorine. So the moles of chlorine. I know I have 0.57 grams of chlorine. I'm going to multiply that by my molar mass of chlorine, which is going to be 35.45 grams over 1 mole. And I'm going to get 0.0161 moles of chlorine. So to find your empirical formula, I'm going to put EF for empirical formula. I'm going to have Hg, and this is how many moles, 0.171, and then Cl, 0.0161. And what you want to do is you want to divide this by the lowest one. So we want one of these to equal 1. So we're going to divide this by 0.0161, 0.0161. And I end up getting, it approximately equals HgCl. So notice that this is a 1-to-1 ratio of hydrogen to chlorine. Now, this isn't the actual molecular formula. It's just the ratio. So if we go back to our previous page and we look at what our 2 possible formulas are, we said that our 2 possible formulas was either HgCl2 or Hg2Cl2 or HgCl2. One of these matches the 1-to-1 ratio, and the only one that matches the 1-to-1 ratio is Hg2Cl2. So if we go back, what we see is that my molecular formula, what it actually is Hg2Cl2. And so that is my molecular formula based off the fact that it is a 1-to-1 ratio. Okay. I'm going to go ahead and move on to number 10. Number 10 is kind of a longer one. Okay. So this is number 10 on the homework. Number 10 says glutamine is 41.1% carbon, 6.9% hydrogen, 19.2% nitrogen, 32.8% oxygen by mass. The molar mass of glutamine is 146 grams per mole. So the first thing we want to do is we want to find the empirical formula for glutamine. So I'm going to organize my data. And remember, one of the things for finding the empirical formula is you want to assume you have a 100-gram sample. So what that means is if I think about carbon, and if I have a 100-gram sample, that means I have 41.1 grams of carbon. I have 6.9 grams of hydrogen. I have 19, whoops, let me go back. Let me label this before I write this down. I have nitrogen, and I have 19.2 grams of nitrogen, and I have oxygen, and I have 32.8 grams of oxygen. So again, the big thing with this is that these were originally percentages, but I assume that I have a 100-gram sample, and so that helps me figure that out. So now what I want to do is I want to figure out the number of moles. So I'm going to multiply these each by their molar mass. So if I know that 1 mole of carbon is 12.01 grams of carbon, which means that I have 3.42 moles of carbon. Going to do the same thing with hydrogen. I know that 1 mole of hydrogen is 1.008 grams of hydrogen. And so this ends up being 6.8 moles of hydrogen. Nitrogen, 1 mole of nitrogen equals 14.01 grams of nitrogen. And that's going to be 1.37 moles. Let me cross out my unit since I haven't done that, just to kind of keep my work a little bit more organized. And then for oxygen, I have 1 mole of oxygen, and each mole of oxygen weighs 16.00 grams. And this ends up being 2.05 moles of oxygen. So if we do this, what this looks like is my empirical formula is C3.42, H6.8, N 1.37, and O, which is 2.05. And again, we have all these different compounds. This one's a little bit more complicated, obviously, because we can see that we have 4 different elements that we're dealing with, but we're still going to divide it by the lowest one. So I'm going to divide each one by 1.37, since that is my lowest number of moles. So I want my nitrogen to end up being 1 if I can. And what I end up getting is C 2.5, H 5, N, and then O 1.5. This still should look a little bit weird because we see that we have 0.5s and we can't have half numbers. So what we're going to do is to get rid of this 0.5, we're going to multiply everything by 2. And so if we multiply everything by 2 to get rid of this 0.5, we get our empirical formula to be C5, H10, N2, O3. And so that is my empirical formula for all this data. And then it says to find the molecular formula for glutamine. Okay, so here's my empirical formula. We know that my molecular formula is going to be something around here. Daniel, I'm not going to go over drawing Lewis dot structures for bonds, mostly because we haven't really used that unless you have an example that you have for homework. So we haven't talked about drawing Lewis structures I'm not 100% sure which one you're talking about. So if you have an example to go off of, let me know. Okay, so we're going to find the molecular formula. In this problem, we are given that the molar mass is equal to 146 grams per mole. What I first need to do is I need to remember that I figured out that my empirical formula is equal to C5H10 into O3. So what I want to do is I want to find the molar mass of my empirical formula. So that's going to be 5 times carbon, 10 times hydrogen, 2 times nitrogen, 3 times my mass of oxygen. And I'm not going to put that all in here, but what we see is that it ends up being 146.15 grams per mole. To figure out what I'm going to multiply it by, I'm going to take my molar mass and I'm going to divide it by my empirical formula mass. What we see is, I think you guys can kind of see this without me doing the math, but I'll go ahead and put it in here, is that 146 divided by 146.15 equals 1/1, which means that I'm going to multiply my empirical formula. I'm going to multiply this by 1. Well, multiplying this by 1 means I'm going to have the exact same formula. So in this case, my empirical formula equals my molecular formula. So there's nothing I have to change. All right, so let's do C for this problem. C for this problem states, what is the number of oxygen atoms in 53 grams of glutamine? So when I start this problem, if I have 53, Sarah, we can't have decimals like 2.5 because we can't have 0.5 of an atom. So when we write out that chemical formula, we have to have whole numbers only. It would be, because we could either say that it's the same thing as having 2.5 moles or 2.5 atoms. Those things are kind of interchangeable. So whenever we have those subscripts, they have to be whole numbers. So you do have to change that to being a whole number. So if we have 53.0 grams of glutamine, I guess I'll write this out, glutamine. I need to convert this into my final thing being the number of atoms of oxygen. Okay, so the first thing I know is I can use my molar mass to get moles of glutamine. So I have 1.46.5 grams equals 1 mole. And I'm going to put a big G for glutamine so I don't have to keep writing that out. That would get me to moles of glutamine. What I now also know, I want to get to atoms of oxygen. So what I need to get is like 2 moles. So let me look at my math. So I know that 1 mole of glutamine has 6.02 times 10 to the 23rd molecules of glutamine. I'm going to put this down here. And I know that for every 1 molecule of glutamine, I have, according to my formula, 3 atoms of oxygen. So moles of glutamine, molecules of glutamine, atoms of hydrogen. So if I were to calculate this, and let me bring out my calculator because I have not calculated this one yet. If I have 53 times 6.02, 23rd, whoops, that was not the right one. Let's see, 53 times 6.02 to the 23rd. And I'm going to multiply that by 3 and then divide it by 146.15. I see that I end up having, with 3 significant figures, 6.55 times 10 to the 23rd atoms of oxygen. And so that's my answer for C. All right. Let's look at some formula unit problems like we have on question number 3 of the homework. I don't want the word formula unit to be confused. Katya, it depends on how many significant figures you have in your problem. So it really just depends. So you want to look at what digits you have. I think the idea of formula unit is kind of confusing some people because the only thing that formula unit refers to is it refers to a compound of an ionic substance. Remember we said that a formula unit equals the smallest ratio of an ionic compound. It is, in a way, similar to talking about a molecule. And molecules, in our case, refer to covalent compounds. They can also be referred to as acids. But so we could have a molecule of an acid, we could have a molecule of a covalent compound. Actually, acids more fall in line under formula units. So let's look at an example. Let's look at C and D. So C says that we have dinitrogen trioxide. And so we have dinitrogen. Whoops. Let me delete that. Dinitrogen trioxide. This is a covalent compound. We can tell by the fact that it's nitrogen and oxygen, which are 2 nonmetals, but also the fact that since we're using prefixes, we only use prefixes when we're naming covalent compounds. So what this tells us is that my compound is N2O3. So dinitrogen, 2 nitrogens, trioxide. Oh, it is tetraoxide. Thank you, guys. Tetroxide. So this would not be 3. This would be 4. Okay. So the beginning says calculate the number of molecules or formula units in 50 grams of each of the compounds. So if we have 50 grams of N2O4, we want to convert this into the number of molecules. So what we want to do is we want to figure out the molar mass. So we want to take the mass of nitrogen. So we know we have 2 times 14.01. And we're going to add that to 4 times 16.00. That's going to give us the molar mass. Wait, is it 14.01? Let me double check. Where is my periodic table? Yeah, 14.01. And so if I calculate this out, I get 28.02 plus 4 times 16. And so what I end up getting is 92.02. So what that means is 92.02 grams of N2O4 equals 1 mole of N2O4. So now I have the number of moles, and now to get the number of molecules, I can use Avogadro's number. So I know that for every 1 mole of N2O4, I have 6.02 times 10 to the 23rd molecules. And so if I do the math and I show 3 significant figures, what I end up getting is 3.27 times 10 to the 23rd molecules of N2O4. Let me just double check that. So 50 divided by 92.02. I'm going to multiply that by 6.02 to the 23rd. Yep. And so that would be my answer. You would do the same thing with a formula unit. So let's look at a formula unit and what that one would look like. So for a formula unit, we could have copper 1 oxide. So copper 1 oxide. When we have copper 1 oxide, what that 1 refers to is the charge that copper has. So this means that we have copper with a +1 charge. Oxide comes from oxygen, which has a 2- charge. So what this ends up being to balance out my charges is going to be Cu2O. So that is my formula unit. Remember, it does not actually have this compound. If we were to look at this, this is just a lowest ratio. We have what's called, a lattice structure with this compound. So if we have 50 grams of Cu2O, and we multiply that by our molar mass, so this is going to be 2 times copper, which is 63.55. And we add that to oxygen, which is 16.00, and there's only one of them. Let me just double check my math. 63.55 times 2 plus 16. Yep, I get that my mass is 143.10 grams of copper oxide, and it's going to be 1 mole of copper 1 oxide. Now, for every 1 mole of copper oxide, we have 6.02 times 10 to the 23rd. I'm going to put F formula units. So we have that many formula units, because again, these don't really necessarily represent molecules. They represent the lowest common ratio. So we have formula units for an ionic compound. And so if we do that math, 50 divided by 143.1, and we multiply that, so that's 6.02, 23rd, we get, I'm going to put this right down here, 2.10 times 10 to the 23rd, and this is, again, formula units. of copper oxide, or copper 1 oxide. And so again, it's the exact same idea, but when we talk about an ionic compound, we need to talk about formula units. We can't talk about molecules because they don't exist as molecules. They exist as a lattice structure of these positive and negative structures, or these positive and negative ions. Okay, let me go back and answer a couple questions that I may have missed, so give me a minute. Are there any? Sarah, I'll have to look for some more practice problems. Your best bet's going to be using the homework, especially since I've given you guys a lot of practice problems on the homework. So make sure you guys are going back over that. Logan, hopefully you understand formula units now that I went over that example problem. There are a lot more example problems on that homework that I gave you that you guys have due tomorrow. So there are a lot more problems and the ideas with that. So definitely look at the homework. Aiden, gases. No, noble gases, the diatomics, except for bromine. Yeah, actually that sounds right. That's a good way of putting it. So we have nitrogen, oxygen, fluorine, chlorine, and iodine. So those would be actually, yeah, and iodine. So those would be our gases. So you definitely want to know those. Ella, you can staple all your homework together. I forgot to give you guys a homework list. I completely slipped my mind. So I'll give some people a little bit more time to get together, but I am going to be collecting all of the homework. So if you want to staple together, you can. Like the ones on the notes for polar, no polar compounds, or do we not need to know those? Let me look back at what you might be talking about, Daniel, because I'm not 100% sure what you're referring to for those. So hold on, let me bring up those notes. It's going to take me a minute. For polar, like the ones on the notes for polar and non-polar organic compounds. Daniel, I'm still not 100% sure what you mean by the Lewis structures for those, because I don't think we've actually done Lewis structures for those. We haven't talked about how they actually bond. We just talked about the idea that one could be a strong nonmetal and one can be a weak nonmetal. So could you maybe look at the homework, the first homework that we did with all those types of bonding, and then ask a specific question, because I'm a little bit confused by what you mean by that. So if it's ionic, we use formula. Yes, Madeline. Ionic is formula units. Covalent is molecules. It really depends on the context. You definitely want to say formula units just because that is the right term. So I might mark off like half a point if you don't use the right term, because then, I mean, you're calling it by something that it's not. So I definitely want to see that you guys have that. Okay. Aiden, number 4 on the homework. Do you have a specific one that you want me to find? So, because there's 4 different ones. So I don't know if I'm necessarily going to do all 4, but if you have a certain one, let me know if you want me to do like A, B, C, or D. Okay, for nonpolar compounds, we should rely more on weak and strong than electron. Yeah, Katya. So we rely on the fact which ones are the strong, because the strong will always be the slightly negative, and then everything else is weak. So if you do that, what is the direct definition of formula unit? Formula unit is the lowest ratio of cations to anions in a ionic compound. So the lowest ratio of cations to anions. Okay, so let's go ahead and look at number 4 on the homework. So number 4, let's go ahead and do something like B. So the equation says calculate the mass of sodium in 8.5 grams of the following sodium-containing food additives. So we would just want the mass of sodium in 8.5 grams of each of the following. So in B, we're given that we have Na3PO4. So this is sodium phosphate. You guys should know how to name this. So the first thing that we're given is, since we are dealing with mass in this example, we definitely want to make sure that we are calculating the molar mass of this compound. So if I were to calculate the molar mass of this compound, I know that sodium, I have 3 of them. And let me look at my periodic table. Sodium, I got 22.99. Yeah, so 22.99 for sodium. And then I'm going to add 1 phosphorus molecule, which is 30.97 on my periodic table that I have. 30.97. And then I'm going to add together 4 times the oxygen, which is 16.00. If I add this all together, I get my molar mass to be, let's see, 163.94 grams per mole. So that's for that whole thing. Now, if I have 8.5 grams of Na3PO4, I can figure out the number of moles. I know that 163.94 grams of Na3PO4, sodium phosphate, is 1 mole of sodium phosphate. And what I also want to know is that for every 1 mole of sodium phosphate, I have 3 moles of sodium. So for every 1 mole of sodium phosphate, I have 3 moles of sodium. It is a 3-to-1. If I have 1 mole of this and I were to break this apart, I would end up with 3 moles of sodium. So if let me just kind of cancel this out as I go along. And then what I know is that if I have 1 mole of sodium, I know that that 1 mole of sodium is 22.99 grams of sodium. And so those units cancel out. And so then I could solve this problem, and what I would end up getting is 3.6 grams of sodium. So if I had 8.5 grams of sodium phosphate, 3.6 grams of that would be due to sodium. Based on number 4 in the homework, will we have to balance the charges of the compounds first, or will they already be balanced? For number 4 on the homework, if they give you a chemical formula, they're already balanced. If they give you a name, you will have to balance it yourself. You should definitely know properties of bonds. I mean, that's just kind of also things that we talked about. A lot of what we talked about in the notes when we talked about ionic and covalent bonds, we reiterated in the lab. So you definitely want to know properties of those. For example, homework 6.1, number 3. Okay, thank you, Daniel, for finding a question for me so I can refer back to that. So let's go ahead and look at 6.1, number 3. Oh, Lewis structures with each atom. Okay, I see what you mean. For some reason, I thought you were talking about covalent compounds, and I was a little bit confused, but now I see what you mean. So let's talk a little bit about this. So what I'm looking at is homework 6.1, and I'm looking at number 3. In a problem like function, do we need to state that there are 3 moles in its own step, or we could just multiply the mass by 3? You do need to show your work. So you do need to show that step because those are the correct conversions. You can't add conversions there that, I don't know. I'm trying to think of the word. You can't add conversions that we don't already know. So we know that in 1 mole of sodium phosphate, there are 3 moles of nitrogen. We can't add that in 1 mole of sodium phosphate that there are so many grams of sodium because that's not a conversion that we use. So you do want to write down each step using the correct conversions and conversions that we have used. Okay, so let's look at one of these. So draw the Lewis structure of each atom and show how electrons are transferred from one form of an ionic compound. So let's look at aluminum and phosphorus. So what you want to do is you do want to look at the chemical formula and you want to, or at the periodic table, and you want to identify how many valence electrons. So I'm drawing my valence electrons in green. So I know that aluminum has 3 valence electrons. And I know that phosphorus has 5. Phosphorus needs 3 more to have the full outer shell. So what's going to happen is that aluminum is going to donate all 3 electrons to phosphorus. So 3 are going to transfer from aluminum to phosphorus. If I were to draw this out slightly differently, what I would see is that aluminum would then have a 3+ charge because it lost 3 electrons. And then phosphorus, with all of its electrons, so I'm kind of drawing these Lewis structures this way, would have a 3-. Since these charges are already balanced out, what we see is that these bond together in a 1-to-1 ratio. So that'd be aluminum phosphide, ALP. Let's look at another one. Let's look at the last one that they have on here. So the last one is calcium, barium, not calcium, chlorine, and barium and chlorine. Okay, so they show it like this, which is a fine way to show it. Again, drawing my valence electrons, I see that chlorine has 7, barium has 2. And so the reason for drawing 2 chlorines is that you see that 1 electron gets transferred to this chlorine, 1 electron gets transferred to this chlorine. So what I end up having is barium with a 2+ charge, and then I have 2 chlorines, so I'm going to put 2 in front, chlorines, which have a full outer shell, and these each have a 1- charge because they each gained 1 electron. So when I rewrite this chemical formula, what I see is that it's BaCl2. And so that is your chemical formula. So hopefully that helps you guys. Difficulty, do you believe? You know what? It's really hard for me to say about the difficulty of different tests, especially since this is the first time that I've given these tests. I think I mentioned this at the beginning of the year that I'm using all new curriculum than I did last year. So it's really hard for me to say about the difficulty of the test. You know, I have a feeling that it's a challenging test because of the math. Just in general, what I see is that students struggle with the math concepts. And we are learning in this chapter a couple big math concepts. The idea of the mole, the idea of molar mass, the idea of setting up your equations using dimensional analysis and things like that. So those big ideas can be challenging. So I want to say that it's a challenging test, but at the same time, we've already tackled some pretty big challenging topics. So I feel like it's on par with the other tests. I wouldn't say that it's an easy test. I wouldn't say that's a super challenging test. I just would say that it's a normal test. I don't know. The only thing you need to know about organic compounds is how to identify them. So just know that organic compounds usually start with a CH. That's all we've really talked about so far about organic compounds. We will end up talking more about organic compounds later in the semester, but right now the idea is just knowing that you can recognize them given the chemical formula. Any other questions that you guys want me to solve or go over? Other questions? It's already been about 55 minutes. I can't believe this time went by so fast. Yes, you do need to still know your ions for sure. Because those are naming. So you'll still have to name on the test, so you'll still have to know your ions so you can name things properly. Is the empirical formula the same as a formula unit in terms of notation? For ionic compounds, they are the same. When we talk about empirical formula, we're usually talking, and the problems that we've done are usually covalent compounds, and so that isn't the same, but for ionic compounds, yes, your empirical formula would be the same as your formula unit. Other questions before we call it a day? How is it not the same? It is the same. So empirical formula is the same for a formula unit. However, for covalent compounds, it might not be the same. Covalent compounds is where it's not talking about the lowest common ratio. We're talking about the molecules. So the formula units only refer to ionic, where when we're talking about molecules, we're talking about covalent. Homework number 11. Let me find that one really fast. Is there a certain part that's on homework number 11 that you have a question for, or do you have a question on the whole thing? Part of the problems are similar to what you've already done. However, maybe the molar mass is a little bit different. Yes, those roots only refer to covalent compounds, Aiden. So those are the only ones where we see covalent compound problems like that on test. Covalent compounds like that on the test, you will see things like on the homework that you guys have, you will see things like number 10. So you want to know how to calculate the empirical formula and the molecular formula given the molar mass. Let me get you guys started on number 11. So this is the homework. We're looking at number 11. And I'm just going to do part maybe A, because the rest of them are similar to number 10 that I already did. However, it talks about finding the molar mass of arginine. So it says a 0.085 mole sample of arginine contains 6.13 grams of carbon, 1.2 grams of hydrogen, 4.75 grams of nitrogen, and 2.72 grams of oxygen. And the first problem, A, says what is the molar mass of arginine? What you want to remember is that your molar mass, remember that fancy M, is equal to the mass divided by the moles. So we are given the number of moles and we are given the individual masses. So what I'm going to do is I'm going to add together all my masses. 6.13 grams. And I'm given 1.20 grams. And I'm given 4.75 grams. And 2.72 grams. So this would be the mass of arginine. I'm just adding up together all the different parts. And then I'm told that the mass, or that this refers to a 0.0850 mole sample of arginine. So this is how I would calculate the molar mass of that compound. And so if you solve for that, what we see is that the molar mass is 174 grams per mole. And so that is how you would solve that problem. You will use this, I think in, let's see, you will use this in part C. And then for part B, you're just going to be finding the empirical formula for arginine. So knowing that you have, this is carbon, hydrogen, nitrogen, oxygen, you're going to convert these into moles, and you're going to find the lowest common ratio. And then you're going to figure out the molecular formula. So this is kind of the weirdest part, is just making this jump from molar mass from all these different masses. So that's what they're asking you to do. Okay. All right. Well, you guys have still homework and things, so practice problems and things like that. On the test, you will, of course, be given a periodic table. You do still want to know all your ions. You want to bring your own calculator that you're comfortable using. And, of course, a pencil. So make sure that you guys are ready. If you guys have some questions beforehand, we'll probably have time before the test to answer a couple of questions as well. So make sure that you guys are prepared, and I hope that you guys have a good rest of your day. I hope this was helpful, and I will see you guys tomorrow. All right, I will talk to you guys later. Bye.